Introduce our plenary speaker, Professor Yuri Tschinkel from New York University. And Professor Tschinkel will talk about equivariant birational geometry. Let's welcome.
Yeah, good morning. So thank you for the introduction. I'm very grateful to the organizers for the opportunity to speak at this amazing Congress. Well, my talk, Equivariant Birational Geometry, could have an alternative title, Groups and Geometry, very much in the spirit of Klein. And some of the things I will show you, well, they're very classical. It's about symmetries, finite groups acting on Delpexo surfaces, Fano threefolds, but there are also some more recent things and more recent developments and techniques that have appeared in recent years that I would like to show you and acquaint you with. So, all right, let's see how it works. I like to start with Gauss. So, do you see a difference? Well, but of course, when you read the numbers, you know the difference. One of them you can construct this compass and ruler, and the other one you cannot. And what is punchline? The realization by Gauss that it's not the symmetries that you see that matter in this problem. It's the hidden symmetries, the Gallo group of the cyclotomic field in the background. And well, 17 is special. And so it's this interaction between, geometry with the symmetries presented to you and the Gallo symmetries that, led to this solution by Gauss of this old problem, which regular polygon can you construct. Okay, so here is something that I found at the University of Göttingen in the library when I was there. Anyway, he had asked some students to make these constructions for 17, the next one, and the next one. So Klein's 100th anniversary of his death was just 3 weeks ago. Klein's approach to group in geometry, of course, well, there are sort of general principles that drove the field forward, but then there are these amazing coincidences, like these very, very special symmetries and groups that come up over and over. And I think that's also part of the beauty of sort of algebraic geometry in small dimensions where you run into these things. So I'll talk about the Klein 4 groups, icosahedron, of course, Klein quartic, Klein cubic threefold. And there's been a lot of recent activity. There is a revival of interest in studying algebraic varieties together with their automorphisms, in particular finite subgroups of automorphisms, in particular finite subgroups of birational automorphisms of projective space. So here is the recent book, Cremona groups, icosahedron, 500 pages by one of my co-authors. Now, so let's start with something very basic. So we have P1 as coordinates, x0, x1. So how can you act on P1 with the Klein 4 group? X goes to minus x goes to 1 over x. Well, does this action come from a representation of the Klein 4 group by projectivizing? So what would that mean? Well, we have 3 commuting convolutions. And if we had the representation, well, 2-dimensional, one of them would necessarily have eigenvalues -1, -1. And when you projectivize, that would collapse. You wouldn't get an action of the Klein 4 group on P1 from a 2-dimensional representation of the Klein 4 group. All right. So to get that, you actually have to go to the dihedral group. And the 2-dimensional representation of a dihedral group after projectivization of that representation will give you that action. Okay, so that's the first thing we see. That's the difference between linear actions on projective space and projectively linear actions, where you have to go to a central extension of the group to get the action. Another thing that we're seeing is that, well, an abelian group acting on projective space doesn't have to have fixed points. Cyclic groups have fixed points, but not. Okay, now, so equivariant geometry, we have a finite group, a G variety Well, it's going to be a pair, algebraic variety over a field. Will work in characteristic 0 and most of the time algebraically closed. But, well, the kind of actions that we have in mind, so there's a Galois action if the field is non-closed. Then you act on, again, by the Galois group, or the geometric action, which will come from automorphisms, embedding of your group into the automorphisms. And I'll focus on birational aspects of these notions in small dimensions. So birational meaning, have a look at, again, birational transformations, equivariant with respect to the group. Now, this view that you should approach these questions, Galois actions and geometric actions at the same time, was put forward by Manin in his paper in the 60s. And so he writes about algebraic case and geometric case. And his main motivation was to understand birational geometry of Del Pezzo surfaces over non-closed fields, with applications to questions in arithmetic, the Hasse principle, weak approximation, and things like this, unirationality. Now, in geometry of the complex numbers, we'd like to understand finite subgroups of the plane Cremona group up to conjugation. And in fact, let me just say that, well, even linear projectively linear actions on P2, the classifications of these actions up to conjugation of the Cremona group is still an open problem. All right. Now, and well, there's been, of course, a lot of progress, but there are also many open questions. So the kind of questions that are central to this field is understanding rationality of varieties. It could be over the complex numbers or over a non-closed field. Stable rationality, in fact, you can have varieties that are not rational but become rational after you multiply this projective space. And then unirationality, that you're dominated by projective space. In all these cases, a necessary condition is that you have a rational point. So existence of rational points is a birational invariant, and so this is required. Okay. Now, what is known for surfaces that are geometrically rational? Over the closure rational, but what about the non-closed field? So rationality is completely settled, and that's, of course, outcome of the minimal model program in dimension 2, as Professor Mori explained in his lecture. You just have to find -1 curves or orbits of -1 curves, Galois orbits of disjoint -1 curve, so that you can contract. And then you contract and you understand where we're getting. Now, stable rationality is still open. There is a list of possible Galois actions. In other words, you know the variety is not rational, but you don't know it may be stably rational, and all non-abstractions vanish. Unirationality is still open in degree 1, even though there are some partial results by color. Conic bundles with at least 8 degenerate fibers. Okay. Now, what about equivariant birational geometry, and what are the parallel notions in this context? So we have a field algebraically closed, characteristic 0, with generically free, that's important, regular action of a finite group G on a smooth projective X. Linearizability, the analog of rationality, would be X is birational to projectivization of the representation of your group. Now, already, over a non-closed field, there's only one projective space in each dimension. In presence of G actions, in other words, over BG, well, there could be different representations of the same dimension, and then are they birational or not to each other, these projective spaces equivariant? In fact, it's not the case. There are examples. Stable linearizability would mean that you multiply this projective space with trivial action of your group, and then you want to be birational to a projectivization of a representation. And unirationality would mean that you're dominated by a projectivization of a representation. So those things should be viewed as analogous over BG to what we're used to over non-closed field K. Now, what's the analogy of having a rational point? Well, in the setup over non-closed fields, the existence of a rational point is a birational invariant. In the setup of group actions, you would guess at first that it should be the existence of a fixed point for the group action G. But that's not the case. Take the simplest non-abelian group, the symmetric group of 3 letters, and look at its action on A2 by a 2-dimensional representation. So the origin will be fixed. Now blow up. So blow up means, well, you have a P1, which is the projectivization of that representation. As you know well, the S3 action on P1 has no fixed points, right? I mean, you switch the poles and you rotate around the equator. So that's the simplest such example. In fact, it turns out that there are models of your variety after some equivariant blowups. All stabilizers are abelian. So there is no chance that you have non-abelian subgroup fixing anything. We work with algebraically closed fields here in the equivariant setup. Yeah. But what is true, however, is that when I restrict to abelian subgroups, I do have fixed points because linear actions of abelian groups have fixed points. And when you blow up that fixed point, you will find fixed point in the exceptional divisor and so on. So for smooth projective varieties, with actions of abelian groups having fixed points is a birational invariant. That should be viewed as the correct analog of having rational points. Okay. Now, so let's go back to our Klein 4 group acting on P1. The condition A, to me, will be there are fixed points on restriction to all abelian subgroups. Is not satisfied in this case, so the action is not unirational, is the definition that I had. So a generically free action on P1 is linear if and only if it satisfies condition A. By Klein, you know what these finite groups are. It's a cyclic group, dihedral, A4 is 4, A5. Cyclic groups, of course, have fixed points. Dihedral groups with 2 times n, well, or n of order 2n, where n is odd, they're also linear, those actions, and all the other actions, well, would contain the Klein 4 group as a subgroup, and therefore not be unirational equivariantly. Okay, so that's the answer for P1. Now, if we allow generic stabilizers, however, that's something that we could have considered from the beginning, and often we have to take into account that even if the action on the ambient variety is generically free, on some subvariety that's relevant for some birational constructions, projection, this and the other, the action doesn't have to be generically free. And then you would have to develop all these notions in that context. There you see that the dn action for even n is unirational. Because, as I told you, representation of D4, you projectivize, you get the Klein 4 group acting on P1, and there is a generic stabilizer. So in D4, those abelian subgroups have fixed points for the projection on P1, while the effective action has no fixed points on abelian subgroups. Okay. Now, what do we know about linearizability, projective linearizability, unirationality of actions on surfaces? And of course, that condition A, existence of fixed points on abelian subgroups, is necessary, so let's look at that. So the linearizability was just recently settled by Penardian, Sarikyan, Jasinski. The stable linearizability, well, there is a lot of progress. For Delpezzo surfaces, there is only one open case. So that's due to Prokhorov. Delpezzo surface of degree 4 with a particular action of this group of order 12. And for conic bundles, of course, we don't really know. And unirationality was settled for generically free actions on Delpezzo surfaces of degree at least 3, so cubics, intersection of 2 quadrics. And there are also counterexamples. So the Klein quartic double cover of P2 ramified in the Planck quartic, where you act with some subgroup of the automorphisms, PSL2F7. Well, that particular action is not unirational while having fixed points on abelian subgroups. So the plan for the talk is I'll discuss some cohomological abstractions, group cohomology, and then I'll give you applications to concrete geometric problems, birationality in the equivariant context, as well as unirationality of Hanus threefolds. All right, so let's start with group cohomology. All right, we have a finite group, cohomology of finite group with coefficients in K star. K is our ground field, close bracket closed, trivial action K star. So you can look at restriction homomorphism, group cohomology, and let's define like B2 of G, the Bogomolov multiplier, as the kernel, so intersection of the kernels for the maps into these abelian groups, subgroups of G. Now, this particular group came up in the study of Noether's problem. So Bogomolov proved in '87 that this purely group theoretic invariant is actually equal to the unramified Brau group of the field of invariance, where V is an arbitrary faithful representation of your finite group G. All right, so there was this question whether or not such fields of invariance are rational, and unramified cohomology is an abstraction to rationality, and Bogomolov was able to produce this simple formula, and then you can ask, well, what kind of groups have this property, and you come up with groups of order 64, 128, so yeah, there is a list. In fact, you can Google under Bogomology, and then you'll find a web page which has tables of these things. Now, we can also consider analogs of this for other cohomology. How about H3 of G with coefficients in K star? Or even more generally, suppose you have a G module M, then we can do the same thing. For example, B3 GM, kernel for H3 GM to with abelian subgroups. Now, it turns out that it's much easier to give examples of groups where the B3 is non-zero. So out of 51 groups of order 32, like half of them have non-trivial B3 of G. And I gave you some of them, and the first one you see is the quaternion group Q8. All right, so this is just background. And how are we going to deploy these things in geometry? So there are some cohomological abstractions that emerge. So if you have a smooth projective variety of an algebraically closed field, regular action of a finite group G, then there is sort of an exact sequence that comes out of a Leray spectral sequence for the G action, which looks like this. So, well, PIC, of course, is familiar. It's a PK group of our variety. I take G invariants. When I have a G action, it will act on everything inside. It will act on the PK group. It will act on singularities. It will act on. Now, PIC XG is G linearized line bundles. In other words, it's a PK group of the quotient stack X mod G. Well, so of course, when you have a linearization, you can change by characters of your group, as always. So that part is clear. So here is this thing. It's called the Ametzur invariant when you work in geometry of a non-closed field, and also in equivariant context. And then you can continue this thing. You get the Brau group of the stack, and that maps into H1 GP car, and that in turn maps into H3 GK star. Now the sequences look exactly the same over a non-closed field, except that it's not going to be a stack. It's going to be geometric, non-trivial part of the Brau group, the kernel of Brau group of the ground field to the Brau group of the algebraic closure. It looks just the same over a non-closed field. But there are some differences. And the differences are, I'll explain in a second, so these two maps of interest to us, delta 2, delta 3, you see, if you have let's say, a rational point of a non-closed field, the image is necessarily trivial. All right? In the equivariant context, a fixed point will force triviality of the image. The group there in this position, H1 GP car, in fact, Manin spent a lot of time studying this, and that paper that I gave you in the beginning, that first page, well, it studies this for Delpezzo surfaces over non-closed fields and its group actions. It's an important invariant. It's a stable birational invariant. So let me explain in a few words why this is a stable birational invariant. You see, if X is projective space, of course, the Picard is Z, H1GZ, well, it's trivial. Now, when you do a birational multiplication, you blow up an orbit, right? You blow up an orbit, you add to the Picard a permutation module. H1 over permutation module is trivial. So blow up, blow down, blow up, blow down, it doesn't change. It is a birational invariant. In fact, it's a stable birational invariant because when you take X and multiply this projective space, you just add Z to the Picard, so nothing happens. So the moment you find a Gallo action or a G action where this is non-trivial, that's an abstraction to rationality or linearizability. And that, because of such an important application, it has been well studied. So all possibilities have been computed. In fact, what are the possibilities? Well, of course, you know the symmetries, cubic surface, Weil group of E6, Weil group of E7. Picard is quadratic form, lattice, so your symmetry has to go through that lattice. So you're basically looking at finite, well, at subgroups of these Weil groups, and well, then you see what happens. You compute for the representation Picard. And so this group vanishes for all Delpezzo surfaces of degree bigger or equal than 5. And then there is a big paper by Kuniavsky, Spragarov, Fassman, where Delpezzo surfaces of degree 4 have been completely described, studied, and so on. Anyway, so this group is known. And, okay, be it over non-closed field or equivariantly, what is a necessary condition for stable linearizability is that this group vanishes, well, not only for the group, but also for all subgroups. Because if you're not linearizable for a subgroup, you're not linearizable for a big group. And so over non-closed fields, there are actually 32 types of Delpezzo surfaces where this sink is 0. And those are candidates for stable rationality. And over BG, there is only one such type, as I mentioned. It's a result of Prokhorov. Now, okay, so we know everything. We know how to compute this stuff. Then we were sort of curious with Andrew. There is this other term in that long exact sequence, namely the Brouwer group of the partial stack. Okay, so people are interested in computing this. Just this week, there is a paper on arXiv computing the Brouwer group of stacky curves. Stuff like this. So we have a general algorithm that does it in case where X is rational. And, well, it's just an algorithm. So you can deploy it. And in terms of the stabilizer stratification for the action. And then, of course, you can ask, well, you have an algorithm. So, well, let's compute. So, and in fact, all actions of abelian groups on Delpezzo surfaces and certain conic bundles have been the Brouwer group for those quotient stacks has been computed in some recent papers following our algorithm. So let's go back to this sequence. And as I mentioned, the images of delta 2 and delta 3 are sort of important. So in this case, it's the Ametzler group. Of course, you've seen it very well. Look at the conic without points. So, well, not every invariant class, yeah, you have 2 points, but you have a note of 1 point. And, well, it's going to be Z mod 2 in that case. And here, so it's an invariant class, but that's not represented by the divisor. And there is this Ametzler 3 that stares us in the face. You see, if you were to deploy these kind of things in the study of rationality or over non-closed fields, unirationality, they would immediately disappear as interesting groups because a rational point will kill it. So there's going to be nothing left. But because over BG, you may be linear without having fixed points, you pick up interesting invariants for G actions, interesting abstraction to linearizability. So the first thing to observe is that both groups are stable birational invariant in the equivariant context. Both vanish if there is a fixed point, and in particular, if there are fixed points on abelian subgroups, then you know where to search for non-trivial examples in those Bogomolov groups that I showed you before. So in both cases, if X satisfies condition A, then the corresponding Ametsa group has to be a subgroup of the second or third Bogomolov multiplier, because of that condition. And if you're unirational, then they both have to be 0. So this is something that, you can then check and look at Delpezzo surfaces, look at all possibilities for G actions on Delpezzo surfaces. And in fact, there is a recent paper that computes the second Ametsa group in all cases. And in particular, you find that if you have a Delpezzo surface of degree less equal than 6, then all these things are 0, a minimal Delpezzo surface. Now, okay, so we're looking at Ametsa 3. We've introduced this. So we want to compute it for Delpezzo surfaces. And so we just compute everything in a recent paper with my student Zhang. And suppose, it's non-zero, the surface is G minimal. Then X has to be one of the following. It's the Fermat cubic with the action of C3 cubed. It's a Delpezzo surface of degree 2 with some actions. But the most interesting one is this one with the action of Q8. So this is the only one where you have fixed points on all abelian subgroups. So the obvious abstraction to unirationality goes away. Of course, every abelian subgroup of Q8 is cyclic, and cyclic actions on rational varieties, smooth projected rational varieties have fixed points. So, well, how do we know that there is an abstraction? Well, we look at the stabilizer stratification. There is some elliptic curve. We compute the Brau group of the quotient. We find that it's 0, quotient stack. And then, well, we know the H2. And in fact, we know the B3 of G for Q8. It happens to be mod 2. That's why we have a chance of producing an interesting example. And we also know that H1 GP car is mod 2. So that's part of all the calculations that people were making this. So projectively means that you're dominated not by a linear representation, but a projective linear action. So it actually abstracts both. I will talk in a second, I will talk about these distinctions, actually an important point. Yeah. So, all right. So over non-closed fields, it would mean that you're not dominated by Brau-Severi variety and things like this. All right, and so this is the only action that satisfies condition A and has non-trivial Ametsa abstraction to unirationality for such a small group. So, linearizability versus projective linearizability. Just the thing you asked. So projective linear actions come from projectivizing the representation of the central extension. All right. Now, so what's the analogy? So linearizability should be viewed as analogous to rationality over non-closed fields. Projective linearizability, it should be viewed as birationality to Brauer-Severi variety. Now, there is a huge literature on studying which variety is rational and so on and so on. There's actually very little that we could find about, well, when is a variety birational to Brauer-Severi variety? I mean, who would even look at this? And in fact, it's very hard to find like non-trivial such examples. In particular, like unirationality has been studied for a very, very long time, non-closed fields. But how about being dominated by a Brau-Severi variety? So, well, projective unirationality, as you were asking, what does it mean? You are dominated by a projectivization of faithful representation of a central extension. So, and as I just said, it's difficult to construct such things in practice. Now, so let me give you like the first example. So condition A, we said condition A is a necessary condition for unirationality. All right. Well, let's produce an action on projective space that satisfies condition A, but fails unirationality. All right. So it's going to be a projective linear action that fails unirationality. So we pick a finite group with a non-trivial B2 of G, that Bogomolov multiplier, a group of 464, and you can find a list of these groups. And you pick a class in this non-trivial class in the Bogomolov multiplier. Now, what are Bogomolov multipliers? So it's some class in H2. Well, there will be a central extension of your group. Okay, a cyclic central extension. And then we just pick a faithful representation of that extension with the property that the center acts diagonally on in this representation. You can cook up such representations. Okay, and then you projectivize. So that will give you a projective linear action of the group G on projective space. Now, what are the properties? You know that on abelian subgroups, your class is trivial because that's how we picked it. So that means that, well, it's trivial. That means it's actually linear for actions of abelian subgroups. Okay, so that means it satisfies condition A. So on every abelian subgroup, you have fixed points on this projective space. But, well, it's not linear because by assumption, right, it's a non-trivial class. So there is a non-trivial Amitsur invariant in this picture, and that prevents unirationality even. So, okay. So it's not stably linearizable, but it's not even unirational. Now, so I want to talk about equivariant birationalities, again in small dimensions. So cubic threefolds, smooth cubic threefolds, it is well known that they are birational to some other Fano variety, degree 14, intersection of Grassmannian 2,6, P9 and P14. So this is well known classically, complex numbers, it's just well known. But much less is known when the ground field is not algebraically closed or when we have a G action. So, well, we look at large groups that can act. There is this PSL2 F11 that acts on the Klein cubic threefold, like a very symmetric cubic threefold. And there is also a distinguished smooth Fano threefold of degree 14, also with a generically free action of the same group. It is birational to the Klein cubic without the actions, but they are not equivariantly birational. In fact, the G actions on both are birationally rigid, and that's not birational to each other. So this is a recent theorem of Blank, Cheltsov, Duncan, and Prokhorov. So we were very sort of inspired. We are looking for examples of varieties that are not birational, but maybe stably birational to each other. So the theorem that we proved last year, this Zhang, is that, well, you have kind of a twisted stable birationality. In other words, you multiply with P2, you multiply with the particulization of a six-dimensional irreducible representation of central extension of SL2F11, and those are birational to each other. I should say that the question of stable birationalities of non-birational varieties of non-closed fields is extremely difficult. There's only one non-trivial example in the literature, very specific Del Pezzo surface of degree 4, where the Galois group XY S3. So like the smallest things that you can imagine. And all examples, all non-trivial examples that we know, can be reduced to that one case. However, in the equivariant context, there's like a huge supply of stable birationalities, because it's just a different world. You know, certain things are harder, but other things suddenly become much more accessible. In particular, these kind of statements about stable birationalities. Now, okay, the group is large, so birational rigidity, so techniques from the minimal model program, work well when the orbits are large. Whenever you look at special loci, you get like a very large orbit. It's very hard to move around, to do things geometrically. Everything is so rigid. Well, then let's look at something smaller. And we find examples where the Klein 4 group acts on the cubic threefold and on the degree 14 Fanus threefold. And the actions are not equivariantly birational, but are twisted stably equivariantly birational. So it's kind of amazing that this stuff can work. I mean, at least to us, it was sort of amazing. How do we know that they're not birational? Well, that's a separate lecture. There are sort of new invariants introduced by Andrew Crash and myself, equivariant Burnside groups that allow to capture the non-equivariants. And then, of course, you need this vector bundle construction to produce these twisted stable rationalities in this case. Something very concrete here. Now, equivariant unirationality. So let's go to non-closed fields, and let's just look at quadric hypersurfaces, surfaces, threefolds, and so on. You need a rational point, and if you have a rational point, you project. So that's the thing. And nobody ever thinks about birational maps from a quadric to projective space. That's not like this. Well, maybe in Fanus threefolds, I mean, people, they have thought, I mean, there are some maps, but in higher dimensions, not really. Now, suppose you have a cubic surface with a rational point that's necessary. How do we know that's unirational of the ground field? Well, that's very nicely explained in Manin's book, Cubic Forms. All right, if you have two rational points, like in general sort of position, you look at one tangent hyperplane section, another tangent hyperplane section, you get singular cubic curves, so it's like P1, P1, and then you get a map, P1 times P1 into the thing by picking rational points on those curves and drawing a line and getting the certain intersection point. So that's a standard construction. And of course, suppose you don't know that you have a second rational point. Well, when you pass to a quadratic extension, you do it over quadratic extensions, then you do some descent, okay? Now, and you can do that in high dimensions as well, for threefolds and so on. So, but in the equivariant setting, you don't have to have a rational point, I mean a fixed point, or an orbit of length 2. So we need some other techniques, technologies to prove, let's say, unirationality. One thing that emerged is sort of, you can actually build a bridge between equivariant geometry and geometry over unclosed fields via torsors. So in this setting, so G is an algebraic group, doesn't have to be finite. So you can make a G torsor, well, over your ground field. Now, what's a G torsor? It's basically a Galois extension of G. Polynomial, non-variable, so that the Galois group is, this G, and it's a finite group. Now, if you have a smooth projective G variety, then you do the following. You take the product of G with your torsor and you take a quotient by the group. So you have a G action here and here, diagonally, and that thing is a twisted form of your original variety, and, well, a twist via the torsor. So this is sort of a construction of twisted forms. Over non-closed fields, again, you can do the same thing. You start with a P1 and you get yourself a conic without points. All right. So here is a theorem of Duncan and Reisan that says the following. Suppose you have a smooth projective G variety over some field, then the action is stably linearizable if and only if for every overfield and every twist via some G torsor of that field, the corresponding variety over that field is stably rational. So this is pretty powerful because we are much more comfortable working over fields than working, over BG, and that allows to, translate questions about stable linearizability to stable rationality. Well, the first thing that you think about when you read this, oh, what about linearizability? Well, it turned out that for linearizability it fails. So now, okay, that's the case. We know what to do for quadrics. Suppose you have a G action on a quadric, then the first theorem of Duncan and Reichstein is that it is stably linearizable, well, if and only if it's stably linearizable for a 2-zero subgroup. How would we read it over non-closed fields? Well, if you have a cycle of odd degree, then that would give you a rational point, and then that would give you rationality and things like this. So you're only interested in degree 2 extensions and so on. Well, okay, and as I said, there may not be a G fixed point in all of this. And the proof of the theorem uses the translation to non-closed fields, which I described. Now, okay, what are the standard constructions that you would do over BG, mimicking? Well, first of all, of course, unirationality is compatible with taking products, and if you dominate, x to y, if x is unirational, and certainly so is y. So, well, then you would like to understand G actions on quadrics. So how would you approach unirationality of a quadric? Now, without a fixed point. If you don't have a fixed point, it could still be the case that the ambient representations decomposes. So if it decomposes, you would have like a sub-representation, and then rather than a fixed point, you would have a sub-quadric. Now, if that sub-quadric happens to be unirational, then so is a big quadric, equivariantly. And in this case, that sub-quadric could have a non-trivial generic stabilizer. So when we say unirational, we really mean unirational with a stabilizer. And so the examples that I gave you, like D4 action on T1, these are the kind of things that show up here. So, and how do we get that unirationality? That's very clear. You pick a point on your subquadric, you look at the ambient space as a projective representation, and then you draw lines. It's certainly equivariant. And then you get a map from S times projective space, dominant map, to X by looking at the second intersection point. And so if this is unirational, this is your representation, an ambient representation, then of course your X is going to be unirational. All right, so how about cubics? Now suppose you have some cubic hypersurface, dimension at least 2, not a cone. Suppose the G action is generically free and you have a fixed point, then it's unirational. And so that's sort of mimicking the original construction. But you could do better. Suppose you have some hyperplane section, a cubic sort of hypersurface in your given cubic that happens to be unirational. Then you have the same thing, that you can prove unirationality for X by moving from this hyperplane section. So again, you're not requiring that the action on that divisor is generically free. And so how do we do it? Well, you can look at the tangent bundle and get a rational map from the total space of the tangent bundle. And then that's... So these are sort of alternative ways of proving, rationality, unirationality, and so on and so on. Now, so here are some basic results. You can have a quadric threefold with an action of C2 squared times S3 that's not linearizable, satisfies condition A. Now, Duncan and Reichstein tell us that stable linearizability can be read off from the 2-zero subgroup for quadrics, and well, the 2-zero subgroup here is going to be C2 cubed, and condition A means there is a rational point, there is a fixed point. That means that for the 2-zero subgroup, it's linearizable. So by the theorem, it's stably linearizable. So, of course, you'll never get it over non-closed fields. You know, a quadric that's not rational but stably rational. For quadric, stable rationality and rationality is the same. You have to have a rational point. But over BG, you have such things. Well, how about the A5 action? You know, you take your 5-dimensional representation. There is a quadric in there, the icosahedral action. So again, birational rigidity tells you, in that sort of recent results, that this thing is rigid, but the Sulu 2 subgroup actually has fixed points. And so it's going to be stably linearizable, but not linearizable. Here's another example. So you see, you get plenty of such examples over BG. How about the dihedral group for n odd? Well, for n odd, of course, 2 Sulu subgroup, I mean, clearly there are fixed points, so for Sulu 2, it's linearizable, therefore stably linearizable. But how about an S3 action on this quadric? You know, how do we act? This is a 2-dimensional representation, so zeta, zeta minus 1, and switching x1, x2. This is a 2-dimensional, and this, you know, just trivial. Well, we don't know whether or not this thing is linearizable for S3. Yeah, it's really strange that quadric threefolds. You think that everything is clear. Anyway, so here is a theorem which says that if you have a smooth 3-dimensional quadric with generically free action of a finite group satisfying condition A, then it's unirational and therefore stably linearizable, because for quadrics, unirationality and stable linearizability are the same. So how do we prove it? Well, we look at everything that can happen. We are only interested in 2 groups. So you look at all possibilities for representations. You look at what condition. I mean, it's a lot of combinatorics, but so sort of at least a clean end result. Now, what about cubic threefolds? Let's say smooth cubic threefolds. So of course, we know those with maximal automorphisms. So here is the one that I talked about previously, the Klein cubic threefold, and then of course the diagonal one, and a few others. So the maximal automorphisms we know, but any subgroup will be somewhere there, and then the equations may look different. You may have more interesting equations. So what do? So we look at non-abelian groups acting on cubics, because abelian groups by condition A will have fixed points, and if you have a fixed point, then it's unirational. So then you look at 5-dimensional representations that will give rise to an action of those groups on cubic threefolds. Of course, you get a list. So we get 541 pairs, cubic, G action, and so on. We check condition A, it fails for so and so many. We check fixed points again. We check fixed points on index 2 subgroups. We look at invariant hyperplane sections. Then all of these cases will give us unirationality constructions. And then there is a result. Suppose you have a cubic threefold satisfying condition A, necessary condition for unirationality, then you are unirational, except, of course, this is nasty because it has 3 in it. And then there are some others, including the Klein cubic threefold that we don't know about, the A5 acting on P4 by irreducible representation of A5. So now, here is the thing, that if you translate this to non-closed fields and use a conjecture to the effect that if you have a cycle of degree coprime to 3, then you have a rational point. That's a conjecture of Corey. Then, when you have a rational point, you prove unirationality. In other words, if you had this Castle, Sonnet, and Dyer conjecture, Corey, I think Corey was also part of that, then you would have unirationality for these actions. Not for this one, because there is a 3 in there, but for these actions, you would have it. But we don't know of any like a geometric construction that will produce it for us. So that would be a nice thing to do. Now, since we understand the smooth ones, what about singular ones? Of course, all singular cubics are rational. We looked at all possibilities for isolated singularities given in a recent thesis of Viktorova. And then we look at automorphisms that can arise. We classified everything inside. And then the theorem is that condition A implies unirationality in all cases. And there are many examples, actually, of unirational ones that fail stable linearizability. Because in those cases, we've also computed the H1G Picard for smooth model of that cubic, and we find many examples with non-trivial H1G Picards. In fact, we find all possibilities for these things in case of singular cubic threefolds, and we've also done non-isolated singularities. So here the theorem again is kind of complete for the singular ones. Now, so I gave you some cohomological abstractions to unirationality, and then we were poking some further, what else can you do? So for non-closed fields, there is the theory of universal torsors that goes back to Colliot-Telen and Saint-Sucre, which of course you've seen many times. Projective space, like P1. So what's the universal torsor over it? It's like A2 minus 0. And it's a torsor for the Néron-Severi torus. Okay, case of P1, it's characters Z, so the torus is GM. You have a GM action on A2 minus 0, it produces in the quotient your P1. But you can do that in general. This is a Néron-Severi torus. The characters of that torus are precisely the Picard, and then you just take a sum of line bundles over your X, and that's your T. And so on that, you have sort of the action. Now, so that's the standard example that you need to see. And so we found that, all right, so you have a G action on X. So if you have a line bundle, you can ask, well, does the G action live to a line bundle? Well, that's sort of the amateur abstraction that we saw before. Is that line bundle linearized or not, an invariant line bundle? But it turns out that you can actually look at all the line bundles together, the whole Picard, and you get a class in H2G Picard X dual tensor K star. All right. And that class, the non-vanishing of that class, is an abstraction to unirationality of the action. So that's the theorem that we proved with Andrew. It's, well, in words, it's an abstraction to lifting the G actions. In algebra, it's some specific class that can be computed, and that we have computed in many examples. So that's the theorem. If the G action is unirational, then the class vanishes. Now, well, we have condition A, right? Unirationality, we need to have unirationality fixed points on abelian subgroups. That means that this class will have to lie in that B2, the Bogomolov thing, for the G action on this particular module. So, and again, here we don't assume generic freeness for the action at all. So there is one class of varieties where the universal torsors are well understood. Well, I give you already P1 and A2 minus 0. If you look at the toric variety, a smooth projective toric variety, then you know that there is sort of the affine space over it, AN, where N is, boundary components, the boundary dividers, and then minus something, it's called subset, like the origin, stable points. And so basically a toric variety is the quotient of affine space by the Néron-Severi torus. So, right, what do we have? What are the automorphisms of a toric variety? Toric automorphisms. Well, automorphisms of a torus, of course, you're going to act on characters. So that's the characters is just a lattice, so it's a GLD of Z. And you can also translate by elements in the torus. So your favorite action, well, anyway, on P1, you can switch Z mod 2, and then you can translate by, let's say, a cyclic group. So now, okay, the theorem is that if you have a smooth projective toric variety with an action of a finite group that comes from automorphisms of the torus, then the action is equivariantly unirational if and only if the class vanishes. The vanishing is necessary, but also sufficient in this case. Now, it turned out that, well, it can be computed. How do you compute it? Well, you see the characters, they're coming from characters as functions, modulo constants, the lattice of characters. I mean, you look at the monomials, and then, of course, you have the sequence PKR, piecewise linear functions, those are the boundary dividers, and the relations between boundary dividers, well, of course, there are functions without zeros and poles in T, this is the M. So if it's two sequences, but now we have a G action on everything inside. So these are sequences of G modules, and when you have two such sequences, you make an X2, and that's a class. So that's a class that's been computed. And in fact, we can analyze this for three-dimensional toric varieties in some forthcoming joint work with Yuri Tschinkel. The point is that, of course, the action on M and on the Picard of toric varieties over non-closed fields has been studied a lot. There are results of Hoshi, Yamazaki, of Kuniavsky in dimension 3. Rationality of tori, of course, everybody is interested in this. But then you need to have a rational point, which means no translations. That means that your automorphisms are all here. But you see, in the equivariant context, you don't need to have a fixed point. And then you have many interesting examples of these kind of actions with translations that are linearizable, stably linearizable, and so on. And it's actually quite tricky to analyze what can happen when you have all these translations on top of your thing. All right, so we've discussed invariant subtractions in equivariant birational geometry, also G birationality and unirationality of Fanus threefolds. Thank you so much for your attention.
Thank you very much for the wonderful talk. Any questions for the speaker?
You discussed this, the Pezzo surfaces at the beginning. What happens for almost the Pezzos? Does it apply as well, or?
So, because you can always turn it into a smooth Del Pezzo or conic bundle, it
Yes.
kind of reduces to smooth or conic bundles.
Okay.
So therefore,
It's no problem.
whatever is known is known from there.
Okay.
For your unirationality results, especially for the cubics, I mean, classically, the cubic is 2-to-1 unirational. Do you have information on the degree of the unirationality?
Oh, no, because of, you see, alternative constructions. In principle, we have that information, but we didn't write it down.
Yeah. Okay.
In principle, we can get it.
Oh, okay. Great. Thanks.
But so the point again is you're forced to produce sort of non-standard birationalities that don't really fit in, this is not something you would do over non-closed fields again.
Yeah, but
you still construct it. And the representation, how it splits, and this thing, that thing, it's constructed, completely constructed. So that's one of the advantages with representations, because it really is like so rigid. Yeah.
Any other questions? If not, then let's thank the speaker again.